Hello, my name is OT. Welcome to Steady Bro, and I'm your bro for life. Today, we'll be looking at how the combined regulation of glycolysis and gluconeogenesis occur within the liver. The basic principle underlying the choice for glycolysis or gluconeogenesis to predominate within the liver is based on a simple principle: supply and demand. If the body needs glucose to the vital organs like the brain, it will support gluconeogenesis. If it has abundant glucose and glucose is not scarce, it will support glycolysis. Within the liver, the regulatory enzyme that decides whether gluconeogenesis or glycolysis predominates is a two-in-one enzyme. Let me explain. So it's a single enzyme with a phosphatase domain and a kinase domain. A phosphatase takes away a phosphate group. Kinase adds a phosphate group. The kinase domain is called phosphofructokinase 2, and the phosphatase domain is called fructose bisphosphatase 2. Now, let's look back. When we looked at the regulation of glycolysis within the liver, I mentioned that this molecule, fructose 2,6-bisphosphate, played an important role by potentiating the activity of phosphofructokinase, and by so doing promoted glycolysis. Now, to decide whether glycolysis or gluconeogenesis is favored within the liver, fructose 2,6-bisphosphate plays an important role once again. This is because the phosphatase domain of this two-in-one enzyme cleaves off a phosphate group from fructose 2,6-bisphosphate to form fructose 6-phosphate and an additional phosphate. When this occurs, fructose 2,6-bisphosphate is no longer able to potentiate the activity of phosphofructokinase, and by so doing, glycolysis is not favored. The kinase domain, on the other hand, is readily able to add a phosphate group to fructose 6-phosphate to form fructose 2,6-bisphosphate and favor glycolysis. The question now is, how does the body decide whether to support the addition of a phosphate group or the subtraction of a phosphate group to move either glycolytic or gluconeogenetic? So this is where glucagon and insulin come into play. When blood sugar level is low, the pancreas produces a hormone called glucagon, counter-regulatory hormone to insulin, and causes multiple signaling cascades to occur. An important one of these is the cyclic AMP cascade. When the cyclic AMP cascade occurs, this results in the activation of protein kinase A. Protein kinase A, by phosphorylating the kinase domain of this bifunctional enzyme, it inhibits its activity, leaving the phosphatase domain active. By so doing, the levels of fructose 2,6-bisphosphate is lowered. That means phosphofructokinase cannot be potentiated to further glycolysis. Gluconeogenesis will predominate in favor the formation of glucose. The activity of glucagon is not restricted to the bifunctional enzyme alone. As we've seen in the regulation of glycolysis within the liver, glucagon also inactivates pyruvate kinase, and by so doing prevents the conversion of phosphoenolpyruvate to pyruvate, and hence impeding glycolysis. When the body has abundant sugars, this triggers the release of insulin. When insulin is produced, it favors glycolysis. It does so by causing protein phosphatase to remove the inhibition that was placed on phosphofructokinase 2, i.e. the kinase domain of the bifunctional enzyme. The resulting conformational change inhibits the phosphatase domain of this bifunctional enzyme. By so doing, more fructose 2,6-bisphosphate is produced, potentiates the activity of phosphofructokinase, and by potentiating the activity of phosphofructokinase, glycolysis can flow. Additionally, both insulin and glucagon exert transcriptional control, i.e. they control the rate at which these enzymes are synthesized. Glucagon will block the enzymes that favor glycolysis and promote those that support gluconeogenesis, like phosphoenolpyruvate carboxykinase or fructose 1,6-bisphosphatase, whilst insulin will block these and favor the bifunctional enzyme pyruvate kinase, phosphofructokinase, the hero and the villain. They always try to counter each other based on the body's needs at the moment. So this concludes the regulation of glycolysis and gluconeogenesis within the liver and how the body decides to go left or go right. Salute!